Hey folks, I'm Dr. G, and welcome to today's lesson, which I'm calling a math warm-up for physical chemistry. So I don't claim that we're hitting every single mathematical concept you'll ever need for physical chemistry, but I'm trying to hit many of the big ones, and maybe do a couple small examples, things like that, to sort of give you, like I said, a warm-up for some of the math you'll need for physical chemistry. Once I release this, I'll probably realize that there are a couple other concepts I want to cover, and in that case, I'll release another one, part 2, or something like that. As is the case with any sort of mathematical subject, you need to practice this stuff, right? It's not enough just to watch someone else do it and say, okay, I see how it went, right? You have to try and do some problems yourself. So make sure you're doing your homework and finding other problems to do. But I think this should be helpful to at least see a few simple ones worked through. Also, I think this is the type of video that works best if you pause frequently and really make sure that you're understanding the concepts, that you're building your own mental model of how this stuff works every step of the way. So use that pause button. And I'll remind you that on YouTube, the J, K, and L key, right? Those are keyboard shortcuts. So K, the middle one, is pause and play. And then J backs it up, and L is the one that will fast forward, right? So basically, J will back up 10 seconds, L will go forward 10 seconds, and K you can use to pause and play. So just kind of keep your right hand on those buttons. Pause as necessary, back up 10 seconds, go forward if you want to move to another part, whatever you need. So I really hope you find this video helpful, and I'll see you in the next one.
What's up, everybody? I'm Dr. G, and welcome to today's lesson, which is a math warm-up for physical chemistry. So first, I'll start with a little joke. I don't know how many people are doing memes anymore, but I don't care. I think they're funny. Summary of physical chemistry. Everything you learned in general chemistry was wrong. Here's 3 pages of multivariate calculus to prove it. Right? I love this joke because there's actually some truth to this, is that, when you learn general chemistry, a lot of times things aren't completely explained to you, and it's not the teacher's fault, really. It's that, the rationale behind, why some things are the way they are, you actually need 3 pages of multivariate calculus to show that. And that's something you're going to see if you keep following through with some of the physical chemistry videos I have on my channel. But, if you're after a mathematical description of how nature works, which is pretty much the whole goal in physics and physical chemistry, is finding the math that describes reality, right? If that's what you're after, it's going to be complicated. The complexity, you can't get away with it. Nature is fundamentally complex. As Neil deGrasse Tyson says, nature is under no obligation to be understandable to you. All right, so on to the matter at hand. I think a great place to start for really any scientific course is, physical quantities. What are they? Well, you have a numerical value and you have a unit. Basically, if you want to say anything, like, oh, this is big, this is small, this is a long time, this is a short time, you should always ask the question, compared to what? Right? That's the whole idea with units, is that it gives something standard that we can compare to. You could say, I'm tall. Oh, really? How tall? Like, and tall compared to Shaquille O'Neal? Well, no, right? You could say, like, oh, you know what a foot is? 6 of those. Okay, that's reasonable, right? That's the purpose of units. In fact, you can get quite far sometimes with units. For example, there's a technique called dimensional analysis, where you can sort of examine the units of what something ought to be and rationalize how something may work. And one of the most interesting examples, and you can look this up online, is that of G.I. Taylor. So basically, some photographs were published in a major magazine, I think it was Time magazine, where they showed the blast of nuclear weapons testing. And G.I. Taylor, basically, they did something to the effect of, finding something standard in the picture, like maybe an image of a Jeep. And they know how big a Jeep is. So then okay, well, how big is that blast? Well, you can measure it in Jeeps then, right? And then you can compare, you can convert the length of a Jeep to something more standard, right? Like meters or something like that. But basically, there was a series of photographs, and the amount of time that elapsed, I think maybe it was time stamped in the image or something like that. They knew how much time went by between the different images of the blast, and they were able to approximate the volume of the blast, and then use that to basically predict something like the blast radius of the weapon, something like that. And then they wrote to the magazine and said, hey, this seems to be the range of this weapon. And And I think the story goes something like basically the FBI or some organization like that was like knocking this guy's door down saying, how did you know that? That's information's classified, right? Something like that. But he just calculated it from the image that they published that was public to everyone. So if you know what you're doing with dimensional analysis and you understand units really well, you can really get a good grip on things. All right, so that brings us to fundamental versus derived units. So let's look at some of the fundamental quantities over there on the left. And we see that, we have things like distance, right, or length. That, the symbol is meter, and it's a length, and it's a fundamental unit, right? There's nothing making up length. If you think about, you can't break that down into any simpler components, right? You could say maybe, there's 12 inches in a foot. But of course, those are just other length units that make up a larger length unit. So that doesn't count. It's really about, what's fundamental. Time, right? Is time made up of something? I mean, perhaps there are areas of theoretical physics where they worry about such things. But, as far as physical chemistry goes, time is time. You can't divide time into anything else. It's not made up of something. Time is time. But then on the right side, we have derived units. And we see, note that there's a column of fundamental units for the derived units, and that shows us what these derived units are made up of. So just looking at one of the simplest ones, area, we see that the fundamental units are meters squared. So you could say, okay, that's made up of one type of unit. Yes, but it's meters times meters. It's not just a single length, right? It's a length times a length. That's meters squared. So that's a simpler example of a fundamental unit. And then, we look at things like, say, force. Then that's kilograms times meters per second squared. So now we've got mass, we've got distance, and we've got time all together, and that makes up force. One that kind of catches my eye is electric current. We see that that's measured in amperes. But if we think about electric current, isn't that sort of like maybe, for example, electrons going through a wire? So, couldn't we say like, well, isn't this sort of like electrons per time, right? That it's a flow, right? There's a flow of current. So it kind of seems like, well, that one maybe at first glance might not make sense. You'd say that doesn't seem fundamental. It kind of seems like it's like, charges going by per time or something like that. But then over in the derived units, notice that we have electric charge, the coulomb. And we see that the fundamental units that make it up are amperes times seconds. So what's going on here, right? It seems kind of backwards, right? Like maybe coulomb should be one of the fundamental measurements, and then electric current should be derived. And to answer this question, well, we have to think about, if you wanted to measure this like in a lab, how would you actually do it, right? You can't like watch a wire and count electrons going by, right? That's not possible. So if you actually think how you would want to measure a charge, well, a reasonable way to do that would be, let's say there's a positive charge and you want to measure how strong is that positive charge. Well, if you have a device in it that if you can bring it near the positive charge and there's electrons in a wire that get pushed away from the positive charge because it repels them, then you could measure the current that was going by, right? You could measure the current a lot easier than you can actually count charges going by. Therefore, the fundamental unit is actually amperes, and the derived unit is coulomb. So that one is kind of unusual in that, although the derived unit in this case is actually kind of the more fundamental thing, it's not when it comes to how you would actually measure it. And units are all about measurements. Now, you may have noticed that I have a couple equations on the bottom left. So work equals force times displacement. Right? So if there's some object that I'm pushing along and I'm pushing with a given force and I know how many meters I went, I can multiply those two numbers and then I know how much work I've done. And if you have any experience with thermodynamics, you might remember that the first law tells us that we can add energy to a system by either doing work on it or heating it. Therefore, we know that work should be in units of energy, right? If we're adding things up and changing in energy, yeah, work is in energy. So let's look at the units for energy. We have kilograms times meters squared per second squared. Okay, well, if we know force times the displacement should work out to that. Well, right above that, we see the definition of force. Force is kilograms times meters per second squared. And of course, if you multiply that by a distance, which would be in meters, that's how you get the kilograms times meters squared per second squared. So that checks out. And let's think about another form of energy, kinetic energy, the energy due to something moving. So that's 1/2 times the mass times velocity squared. So again, if we look at the energy and we say, okay, well, what is velocity? Well, velocity is meters per second, but it's velocity squared. So that's actually meters squared per second squared. And then, of course, if we look at the units for energy, it's kilograms. So there's the mass, 1/2 m. And then v squared, yeah, meters squared per second squared. That's velocity squared. And of course, the 1/2 is just a unitless constant, so we don't worry about that. There is no unit associated with that. And you may have noticed that some of these, under the column that says unit symbol, well, that's because, again, sticking with the example of energy, we might not want to write out kilograms times meters squared per second squared over and over again because energy measurements are something that we have to deal with quite frequently. So we just call that a joule, and then it's called J. So the fundamental unit of a joule is actually kilograms times meters squared per second squared. It's just a lot simpler to write J for joule. All right, so another mathematical concept that is often taken for granted, but I like to cover and just remind everyone briefly what it is a function, right? So what's a function? Well, I like to think about functions as being similar to like a little machine. And that machine takes an input and it does something to that input and then it has an output. And the machine also has parameters that you can change, right? So the example that I have here, f of x equals k times x minus s squared. So the input for that is x, right? You give it an x value. And then what does it do to it? It subtracts s from it, squares that, and then multiplies whatever that is by k. So k and s here are parameters for the function, right? So this would be, if an equation has a constant in it, something that's not varying, that's something that uses a parameter. And, maybe from one problem to the next, maybe you can change a parameter, but then basically you just set it and leave it alone, right? It's not changing over time, right? That's what the input is doing, right? As the input is x here. And so the input is usually called an independent variable. And then the dependent variable is the one that comes out, right? So if I take a 1 and I pass it to the machine, there we go. It outputs a 0, right? And then you give it a 2, and then it outputs a 0.5, right? This is kind of how I like to think about a function. It's like a little machine like this. And so again, just to remind you, the input is the independent variable. The output is the dependent variable. And k and s in this particular example are parameters. So anything that like maybe you could change, but once you set it, you leave it alone, and then it just kind of runs over all the values of x that you want to give it, and it outputs all the values of f of x that it calculates. So this is basically how I like to think of a function. So up next, we are going to work with functions a little bit more. And for this, there's actually an interactive tool that I would like you to download so that you can play with it along with the video. So if you go to my website, which is just jeanmarc.com, and you click on the Teaching Tools tab at the bar at the top, it'll take you to this page. These tools that you'll have like little sliders that you can move back and forth and things like that, they're totally free to use. You just have to install the Wolfram CDF player, and there's a link to that on this same page. The way it works is similar to Adobe's business model, right? Where, you have to pay money if you want to get the software to do fancy edits to a PDF, but anyone can read them for free if they download the reader. So Wolfram has done the same thing where they have a computable document format, right? That's what it stands for. So that basically you download this player for free, and then once you download the player, if you download the particular CDFs that I made, you can open them and work with them. The same way that you could open up a PDF if you have a PDF reader. All right, so I've got the Wolfram player open now, and so let's work through this. So what are the independent variable, the dependent variable, and the parameters for this equation? Okay, so here's the equation down here. All right, so we got minus 2 times x plus 2, and then the whole thing squared, right? So the plot actually shows two functions. One function here in blue is f of x equals x squared. So you see, that's right here. So that's f of x equals x squared is this one, right? And then the other one is s times basically x minus t squared. So basically, I can move these things around, t and s. So as you can see, I can change these things, right? But the function is here, right? The function is here, right? It's plotting y equals x squared, right? And this one is plotting s times x minus t squared. So these things are actually the parameters here. So as you can see, I'm changing them a little bit, but the function itself is locked in once I choose a value. So this is what I mean by a parameter in a function. All right, so the next question says, move the sliders until the red function overlaps the blue one perfectly. All righty. So if we move these around, we can see that this kind of moves it left to right. This one kind of changes the way this thing is kind of sloped. So let's try and line these up perfectly. So that's pretty close, a little off. Okay, so it looks like t should be 0 and s should be 1. I think that's supposed to be, there we go. Got it. All right, there it is. So you see that there's some numerical precision things here, right? It's 10 to the negative 16th. We're going to call that 0 for practical purposes here. So we've lined it up, right? So this is basically if t is 0 and s equals 1, then these functions are equivalent. Well, is that surprising? F of x equals x squared. Okay, well, if s equals 1 and t equals 0, this is f of x equals x squared. So this is an example of how we can, tune parameters to produce some sort of function that we're after. And there's examples of this throughout the scientific literature. So like, for example, when you get to the lecture on the quantum mechanics of the hydrogen atom, you'll see that someone found an equation for figuring out the relative spacing for the emission spectrum of hydrogen. And then, of course, that relative spacing could be tuned by multiplying that function by a constant. And so basically, you find the constant that dials it in just right. It's kind of a similar thing to this. All right, so moving on. This particular function here, right, this s times x minus t squared, I chose that because this functional form can actually be used to model the behavior of a spring. Right, like a spring that you compress it and it kind of fights back, and you stretch it and it fights back. Same sort of thing. Remember the potential energy of a spring, 1/2 kx squared. So if we set s to 1/2 and or 1/2 times k, whatever our k value is, and then the t. So what's the physical meaning of that? Think about that for a second. What could that be? One common way to define this is that t, which is usually called x naught. I just chose these letters for whatever reason, but typically it's written as x naught, right? X with a little 0, and that is the length that the spring wants to be. That's basically the idea, is the equilibrium length of the spring, and this can be used for chemical bonds as well. In fact, in molecular dynamics simulations, there is this type of approximation in there. There's definitely some more technical details in there, but potential energy functions of this form do show up in molecular simulation software. All right, so up next, I'd like you to take a look at the derivative demo teaching tool from the same website. That's jeanmarc.com, and then just go to Teaching Tools. So make sure you've downloaded the derivative video CDF for this next part. All right, so I've got the derivative demo CDF open on the same screen as the slides so that you can see what's going on, right? This is what you should have, is this thing right here. And first, let's just play around with the sliders a little bit, right? You can move the x back and forth. You can move the delta x a little bit, right? So pay close attention. Let's put x right here. So x is the red ball, right? That's the position of x at any given moment, right? So I can choose that, whatever I want to set it to. So I'll put it here for now. And now delta x, notice if I set it equal to a negative number, it's a little bit to the left of the red ball. Positive numbers, a little bit to the right of the red ball. So it's going back and forth like that, right? So, so delta x is a small change in x. I guess it doesn't have to be small, right? I can move it all the way out here if I want to. It's some change in x. And then x, of course, is our reference, where we want to be. All right, so now I'd like you to try and think about this for a moment. What do you think I'm trying to show you with this thing compared to the definition on the left there of a derivative, right? There's different ways to define a derivative or sort of derive what it is. But if we look on the left side here, this equation, we say the limit as delta x goes to 0 of f of x plus delta x minus f all over delta x, right? So think about, what a derivative is, right? If you could say, what's a derivative in one word? You'd probably say slope, right? It's the slope. At any given point, it's the slope on that line. And when I first learned about slopes when I was a kid with linear functions, right, the derivative of a linear function is just whatever its slope is, because it is a constant slope. The way I always learned it was rise over run, right? So rise meaning like in the up and down direction, how high are we, right? The y, the dependent variable, y or f of x. So that's what we see at the top is we have some change in f of x that comes about from giving it a slightly different independent variable. So we give it x plus a small change, right? And then we divide it by that small change. And that small change is the change in x. So that's the run. That's how far we've changed in the x direction. So rise over run. This is the definition of a slope, of a linear slope. And of course, we say that for a function that's not linear, this is going to be correct in the limit as delta x goes to 0. And so that brings me to the next question. How do you get the most accurate approximations for the slope using this GUI? Well, if we play around with it, right, and I move by the way, we can visualize the slopes as the exact slope is shown in red, right? So everywhere we go, that is the slope that, like, if the function were a linear function at that point, they would have the same slope, right? So you can see how, like, if I put x here, just pay attention to the red line for a moment. If I put it there at the top of that hill, right, that's flat there. So you can imagine that, you know, if you're very careful, you could balance something up there and it would not roll down, right? So something could remain like stationary there, right? So that's flat right there. And so looking at that red line, yeah, that looks pretty flat straight across. It might be slightly off, you know, because I'm moving this thing around by hand here, but you get the idea, right? That there's different, wherever I am here, the red line shows the true slope. So what does the cyan line show? Well, that shows what the slope would be connecting the cyan point, right? And cyan is like that blue-green color, half blue, half green. That's cyan. So if I were to draw a line from the cyan dot to the red one and connect them, that is what I see there. That's the cyan line. So you can think of that as like trying to approximate the slope. So, you know, looking at this, we see that these slopes are pretty close here. And then if I move this delta x a little bit more there, now they're real close, right? So now if I move this along, boy, they line up really well there. They're pretty close there, real close there, right? So you can see that the most accurate approximations for the slope happen when we take a very small step, delta x, right? So I moved it around a little bit. This is the smallest I could get it with moving that thing back and forth, right? Minus 0.008. So it's a little different, but it's very, very small number. So our delta x is you know, it's there. It's not 0, but it's very small. And look how close these slopes line up. As I move it, you can barely see it by eye that they're even different. So basically, this is a visual confirmation of the limit above. As delta x goes to 0, this statement is correct. It is the slope, even for a nonlinear function, in the limit as delta x goes to 0. All right, so now my next question. Are some of the regions of the function more sensitive to the size of delta x than others? Well, let's make it a little bit bigger, right? Because this is a really small delta x. Yeah, let's put it like right there. So it's 0.04 now. Still pretty small, but not as small as before. And now, so if I move this around, watch the two lines and see where they line up best. That's pretty good, right? That looks really close. If I put it here, that's kind of terrible, right? That's a pretty bad guess at the slope. And then it starts getting good again. That's really good, right? So think to yourself for a moment here. What do you think it is about these different regions of the function where the approximation gets better or worse? Why are some of them better than others? And I encourage you to, pause the video and really think about these things. Don't just wait for me to give you the answer. Well, the reason some areas of this function are better than others is because they're closer to linear, right? Because this is, really this is a linear approximation to the derivative. It's not exactly the derivative. It's a linear approximation. And the approximation gets better and better the smaller delta x gets. But it also gets better in some parts of the function compared to others because it does the best in the flattest parts of the function, right? So if we look where the red ball is right now, right, it's at x equals minus 1.5. Function is super flat there. Here, I'll pull it away so you can see it. You see how flat the function is there? It's almost kind of it's quite flat. And so that's why the approximation is so good. Even, I bet I can make this bigger. Yeah, look at that. I've made the delta x all the way up to 0.16 now, and the approximation's still quite good, right? So like if I move x back here now, there, that's a terrible guess now, right? These slopes are completely different. But now if I put it here again, right, we see that it's quite good, right? It does a good job approximating the slope in this area right here. There we go, right there. It's great, right? That's a really good approximation. But you saw how bad it was at the curvier part. And so basically we're saying that a linear approximation to a derivative of a curved line is better when the curved line looks more straight. So it's actually kind of intuitive. It's quite intuitive. But I think it's nice to see it firsthand like this. And this sort of approximation comes up all the time in physics and physical chemistry, because there are times when there are functions that are not linear functions, but we approximate them as being linear because we zoom into a portion of the curved function that is so close to straight, we can treat it as if it were straight, even though it isn't, and get answers that are still quite good, right? So we have to be clever about how we make approximations, because we can get a lot more done if we're willing to make some approximations. In fact, we really have to make approximations in any sort of work where we're trying to develop equations that represent reality in some way. All right, so moving forward with our mathematical demonstrations, I'd like you to please open up the integral demo CDF. So again, same website, just download the one that says integral demo. All right, so now I have the one that is labeled integral demo, right? So here it is right here. I've got it on the same screen as the slide so we can see it. And again, let's start by just playing with the sliders and see what they do. Play around with it, have fun, just see what it does. So hopefully you have developed some intuition for what these sliders are doing, right? So x min, x max. So that sets the limits of integration. What's my x min? What's my x max? Right? So like the equation on the left here, x min would be A, x max would be B. And then if we look at box count, so if I leave x min and max where they are and I move box count, see these rectangles under the curve here, or between the curve and the x-axis. So if I make it really low, there's very few. There's 10 boxes, right? So that's how many boxes we have. Now there's only one, right? So I could put a whole bunch of them, or just one, or whatever number I want, right? I can put these boxes here. So that is what the little learning tool on the right here is doing. So at this point, maybe pause the video for a few minutes and see if you can anticipate what it is that I'm trying to show you, right? With that integral on the left side of the equality there and the sum on the right. Well, I'm trying to show you the relationship between an integral and a sum. Basically, similar to how I was showing you with the derivative, that we could approximate a derivative using a linear approximation, especially if we take a really tiny step in the independent variable, right? If we take a really tiny step with the independent variable, we found that the approximation, the linear approximation for a derivative got quite good, particularly if it was in a region where the function was pretty flat to begin with, right? The function was closer to linear anyway. So this is kind of a similar approach, but basically what I'm showing you, let's start with the sum actually. We'll start with the right side. So we're summing from I equals 1 to n of f of xi, right? So that's, we're trying different values of x. So different individual values of x, in fact, n values of x, right? That's why we have the n up here, right? So if let's just for a moment say they're integers, right? It's 1, 2, 3, 4, 5, 6, 7. If n equals 7, those would be the numbers that we're plugging in as x of I here. So that's what x of I is. Okay, well this is f of x of I. So that just means plug x of I into this equation that we're trying to integrate. So in this case, this function f of x here is defined on the screen on the right here. So this is basically saying, like, you know, choose a value of x, right? If you plug it in there, all right, x to the third, x to the second, x minus 1, right? All of that, you'd plug it in there. So that's what we're saying is this function that's inside the integral, that's just what this f is. Okay, so what's delta x? Well, delta x is, again, a tiny step forward in the x direction. So it's a small change in x. So now take a moment here and look at x min, x max, and box count, and see if you can tell me which of those parameters is related to delta x. If you're thinking box count, you'd be correct, right? So if we look at this box count, let me set it to a lower number to start. So right now our delta x is pretty large, right? Look at the width of a box here. It's not quite equal to 1, but it's pretty close to it, right? Because there's -2, there's -3. It's like maybe, I don't know, 3/4, something like that. It's around that number. So that's the width of the box. That's our delta x here. Okay, so if we think about a width, delta x, multiplied by f of x, well, what do we call that for the slope? Remember I was talking about rise over run? Well, f of x is how high are we? Okay, width times height. What does that sound like? Think like the really early math class that you've probably taken, right? That's the area of a rectangle. It's just the area of a rectangle, right? It's just height times width. That's what f of x of I times delta x is. Okay, so I'm adding up the area of a bunch of boxes here. Okay, and notice the limit as n goes to infinity. Okay, so if I'm looking within the same region of x min to x max, but I want to have an infinite number of boxes, what do I need to do to the boxes? I need to make them get real skinny, right? I got to pack them in there. So as we can see, if we increase the box count, we get more and more boxes. So now if we turn our attention to the left side of the equation, we have the integral ranging from a to b of f of x dx. Well, f of x, that part is the same. We're looking at the height of the function at x. Okay, so that's a height. So then dx, that's a small change in x. That's also a width. But dx, right, that's an infinitesimal change. That's how we define that in our calculus classes, right? We call that an infinitesimal change in x. Well, n goes to infinity of this. The way to pack those in, really skinny boxes. So as the width of the box goes to 0, right, that's what we've got here, right? I could have just as easily written as delta x goes to 0 instead of n goes to infinity, right? I could have gone either way with it, right? So the more boxes I pack in here, the better the approximation should get. And perhaps you remember that, just sort of a real simple explanation of what's an integral. It's the area under the curve, right? And of course, if it's area below the x-axis, that's considered negative area, right? So that's what we have here in the integral. And, intuitively, you can look at this and say, like, okay, if I'm approximating the area under this curve by adding up the area of a whole bunch of boxes, if I have a bunch of real skinny boxes, that sure looks a lot better than this, right? So if we look at the approximation with 26 boxes here for this particular region that I've chosen at random here, we see that the actual integral is 0.057524. And the numerical integral doesn't even get the sign correct, right? It's minus 0.17 whatever, right? But if I crank up the number of boxes, it's still maybe not great, but it's a lot closer, right? 0.0276. It's at least getting to the right number of decimal places. And if we kept putting more and more boxes there, it would get better and better. And it turns out that taking integrals numerically is something that we do all the time using computers. There are more precise ways to do it than this, right? Like if you use trapezoids instead of rectangles, that gets you a better result typically. And there's a bunch of different ways that you can approximate integrals by adding up the area of shapes that we easily know how to take the area of. So now my next question is, how would you go about doing this type of approximation by hand? Well, you would have to draw a bunch of boxes and, try and keep probably the width the same every time so you don't have to keep measuring that, right? Keep doing the same width, measure the height. You could do that over and over again and just add up the area for a bunch of boxes. And of course, we've kind of already talked about this at length as well. How could we make the numerical approximation of the integral more accurate? Well, more boxes, right? The more boxes we can pack in there, it's going to get more accurate. And of course, there's different numerical techniques. Like if you look up the trapezoid rule, you'll see a way to do it with trapezoids that's better. Simpson's rule. There's a few of these things. So I encourage you to look these things up if you find that interesting. Alrighty, so up next, let's do a review of a few of the mathematical relationships that we'll need for PChem. So here we have a list of some of the exponential laws and logarithm laws. And, some of these you can actually intuit one from the other. For example, x to the a over x to the b. Well, if you know that 1 over x to the b is the same as x to the minus b, you could have brought that up, and then you'd have a minus b that way, right? So there's little things like that. So just make sure you make sense of them and memorize enough of them so that you know them automatically. You shouldn't have to think too hard about these things. It's sort of like, when you're practicing arithmetic, right? Like 5 times 6 is 30. Sure, you could add, 6 5 times or something like that, right? If you want to prove to yourself that 5 times 6 is 30, but it makes more sense to just memorize that 5 times 6 is 30. It's a similar thing here. So just memorize these relationships. Make sure you know them quickly. Quiz yourself on them. So, I highly encourage you to, maybe make a screenshot of this and hang on to it, something like that. So you're going to be taking a lot of derivatives in physical chemistry as well. So I've put together a collection of some that you see very frequently. Of course, the exponent rule, that's always the first one you learn when you learn derivatives. There's some derivatives of the trig functions. And again, it's just something you have to memorize, right? Sometimes you just have to memorize something. The derivative of sine is cosine. Just know that, right? So yeah, exponent and trig derivatives, just make sure that you know how to apply these rules and then you memorize the relationships you need to memorize. Or that, the derivative of the natural log of x is 1 over x, right? So the same thing with the middle column. I would say all of those are just common derivatives that you should have memorized. So if you don't have them memorized yet, that's okay. Just start memorizing them now. And finally, that column on the right with the chain rule, the product rule, and integration by parts. We're going to spend more time on those because those are more procedural, right? Like the chain rule shows you how to take the derivative of functions that are they remind me of, those Russian dolls, the nesting dolls, right? Where you have a doll inside of a doll inside of a doll, right? That's the chain rule, except you have functions inside of functions, right? If you have the sine of e to the x, and the e to the x is inside of sine, right? Something like that. And the product rule, that's more like if you have two functions multiplied together, how do you take their derivative, right? Like maybe e to the x times cosine x, right? That would be an example of when you would want to apply the product rule. And finally, integration by parts. Integration by parts is kind of the trickiest of those three because the first two are kind of more procedural, whereas integration by parts is more strategic. You have to kind of see it as a way to reframe a problem with more than one function inside of the integral so that you can break it up into two functions. And I'm going to do an example of all three of these. So if any of those were a little fuzzy, I encourage you to just keep going and watch the examples of them. All right, so first we're going to do the chain law. And at the top left, you see that road sign. That's actually somewhere in Colorado. And every time I drive by it, I kind of crack up because, it says chain law enforced. They're referring to the laws about using chains on your tires in the snow, right? Because they can mess up the road if there's not really much snow on there and you're wearing the chains. I don't know. They make laws about the chains, when you can wear them. But I always think of the chain law from calculus every time I see it, and it kind of cracks me up a little bit. Anyway, let's apply it to that function right there. So y equals e to the sine of x squared. So this is kind of three functions, right? You've got an x squared function inside of a sine function, but that's inside of an e to the x function. One way to describe functions like this is to say that they're nested. You have functions inside of functions. And of course, if you were to pass a number to a function like this, the first one to operate would be x squared, right? You'd square the number, then you'd take the sine of it, and then you'd exponentiate it. So always remember, functions like this work from the inside out. And whenever I see functions like this, I always think of those Russian nesting dolls. So anyway, we have to split this up. So if you look underneath that, we have y equals f of u. So we're going to make up a variable. We're going to call it u. And we're going to say that's e to the u. So basically we're looking at, remember I compared this to those nesting dolls, those dolls inside of dolls, right? This is the outermost doll. We're saying that's e to the u. So we're just going to call whatever's in the exponent as u for now. Okay? So now let's define what u is a little more carefully. So the next line we say, okay, u is going to be g of v. And so that's just the sine part. So now we're only looking at the sine doll, right? That's kind of the middle doll in this scenario. We're thinking about this like dolls, right? And then, okay, so we're saying sine of v. Well, what's v? We'll call that h of x, and that's going to be x squared, right? So now, like, we can say that y equals f of g of h of x, right? So we've got these functions, one inside of the other. The h is the innermost function, the g is outside of that, and the f is the outermost one. And of course, we've just gone up the alphabet, right? f, g, h. All right, so now we've defined how we want to split everything up, right? We've sort of identified what functions are inside of other functions. Let's move on and start applying the chain law. Well, let's see. Basically, if we go back to what the chain law is defined as, right? The chain law, right? dy dx equals dy du, du dx. And so one way you can kind of look at that, and mathematicians may tell you it's not exactly true to look at it this way, but it works out. If you notice on the right side of that, you see how the du's cancel and you get dy dx? You can think of it that way. And so you can actually do this with as many nested functions as you want, right? You can have 16 functions, right? Where one is innermost and then when the next innermost, right? Right? You could keep going with it. And that's what we're going to do here. So we say like, okay, dy du, right? Because this is f of u. Then we do du dv, right? Because that's v. And then dv dx. So you can see, I'll skip ahead for 1 second. You see how we can line all of these up? The u's canceled, the v's canceled, and you're left with dy dx. That's the strategy. That's what we're doing here. So let me go back. So this is our motivation, right? We're trying to get to this at the top right here. And we do that by defining these individually. So we say, okay, dy du. Well, that's over here. Y is just e to the u. So and this is y. So dy du is just the derivative of this with respect to u. Well, that's the exponential function. It's its own derivative. So that's eu. Okay? Next, we go du dv. So we look at this line here. So du dv. So du dv, we just have to take the derivative of sine with respect to v. So the derivative of sine is cosine. So that's just cosine of v. And then in the end, we look at dv dx. So v is here. This is a function of x. So the derivative of x squared with respect to x is just 2x. So we've taken some known derivatives that were on that table from the previous table, right? And now we just have to put them all together. So as we see, we just multiply. See how I have dy du, du dv, dv dx here. Just write them all out. Du's cancel, dv's cancel, and you're left with dy dx. So eu times cosine of v times 2x. So that's our answer, sort of, right? So what's wrong with it? Well, we've made up two variables and that are sitting in there, and we really want dy dx, right? We don't want u's and v's in there and stuff. So how do we get rid of them? Well, we know what u is. Look, this is u. U equals sine of v, right? We know what v is. V is x squared. So let's plug some stuff in. So here, we've replaced our v with an x squared. And then here, we've replaced a sine of v for our u, right? Because we had e to the u. Well, that's sine of v. Put that in there. All right, we're closer. We got one v in there. We got some x's and a v. So we got to get rid of that. Well, what's v? There's v. V is x squared. So we put that in there, and now we have the answer. So this is how the chain law works. And of course, as with anything in mathematics, it's not a spectator sport, right? You have to learn how to do it yourself. So make sure you do some practice problems with this as well. All right. So now we're going to look at the product rule. So this is how you take a derivative of a function that can be thought of as two functions multiplied together. So we see the definition at the very top there, and we're going to demonstrate it on this function. F of x equals x squared times the sine of x. So clearly one of our functions is x squared, and the other one is sine. And so here let's define u equals x squared and v equals sine. What's u and v? Well, this is what we're doing up here, right? We're getting this from the definition. So if we do this, we say, all right, we're going to call u is x squared, v is sine. Then we're going to take our derivatives, right? So just follow along with the rule here, right? We need du dx, so we take du dx. And then we need dv dx. We got dv dx there. Then we really just need to plug everything in. So we have all of our u's and our v's and our du dx's and everything. So just follow along with that and plug in all the stuff that we got over here, and you've got it. That's it. That's the product rule, or at least that's one example of the product rule. Like this can get much more complicated, but this is one simple example. All right, up next we have integration by parts. So up at the top right, we have the sort of rule for applying integration by parts. It's sort of the guideline for applying this strategy. And the function we are going to take an integral of using integration by parts is shown there. So the integral of the natural log of x over x squared dx. So basically, the tricky thing with applying this is you have to decide what's going to be u and what's going to be v. Now, if we look at the left side here, we have the integral of u dv. So we have to decide what's going to be u and what's going to be dv. And notice it's not uv, it's u dv on the left. So what's that going to be here? And then basically what happens is that when we write the other side, So this expression is a true expression. And you'd say like, well, why would I take a one integral and write it as, the product of u and v minus another integral? It's just another integral. So, well, the idea here is that hopefully, if you've applied this correctly, then this integral on the right side is an easier integral to do than the one on the left. So that's the strategy with this, right? You still have to do an integral, but the idea is that looking at the one on the left, you're like, well, I'm not sure what this is, but if I can express one function inside of it as being u and the other one being dv, well, then I can rewrite it this way, and then I'll do it in such a way that v du is an easier integral to do than the integral of u dv. So that's what we're after here. And so for this particular example, we say, so let's walk through the example and then we'll try to justify everything as we go. So if we choose the natural log of x as being ux, well then dv must be 1 over x squared. So that's what we do here. And so then we say, okay, now looking at the right side, all right, I need this du here. Well, du dx, if this is u, the derivative of the natural log of x is 1 over x. So du dx is 1 over x, and I want du, well, then I can say that du equals 1 over x dx. Right? If I just multiply both sides by dx, I get 1 over x dx. Now I've figured out what du is. It's 1 over x dx. Cool. So now I need v. Well, we know that dv dx is this. So if I integrate that, if I integrate dv dx, and well, if dv dx is 1 over x squared, I plug that in. So then I have to take the integral of 1 over x squared dx, which of course is minus 1 over x. So basically I have to ask myself, all right, the derivative of what gives me 1 over x squared? Well, this is x to the minus 1, so the minus 1 comes out front, cancels out that negative sign, and then the exponent goes down by 1, which is 2, right? So this would be x to the minus 2, right? Or otherwise known as 1 over x squared. So yeah, that checks. So now we have a definition for v is minus 1 over x. We have a definition for du. It's 1 over x dx. So now we can write this thing. And also we have a definition for u here, and we have a definition for v here. So we can write that whole thing. So let's plug everything in. Take just that right-hand side and plug all this stuff in. So now that we've plugged everything in, let's try and take this integral, and hopefully it's an easier integral than the one we started with, right? Because that's the whole point of applying this strategy. And sure enough, it is. We just have to take this integral, which actually we've already done that integral here, right? We already know what it is. And then, of course, minus log of x times 1 over x. That's just this uv part. We don't even have to do any further calculations with that. So then we just take this integral that we already knew what it was, and then we get our answer here. So in retrospect, looking at this, what have we done? We started with an integral that we were not sure how to do, and we found a way to write it as one that we definitely do know how to do. So, the thing we had to recognize here is that, polynomials we like, right? Integrals and derivatives of polynomials, these are our friends. But there was this natural log function in here, which we know if we take the derivative of, that puts us into 1 over x, and then we're kind of in polynomial land and we're happy again. But it's integral we don't like. So basically we looked at it as saying like, well, I wish I could get this log function out of my integral and replace it with its derivative, right? Because notice how we have v right here, right? So notice how we have u outside. The one that you choose for u, you get to pull out of the integral, right? It ends up out here. And then the thing that gets replaced inside of it is its derivative. So basically it was like, well, I'm not sure what to do with the integral with the log function in there, but if I could just pull that thing out and instead have its derivative in there, which is 1 over x, that'd be so much better. So that's sort of the strategy, how you can sort of think about this. And honestly, the Wikipedia page is pretty good for this. I took this example from there, so I have that linked below as well. All right, so the next mathematical topic for physical chemistry that we're going to cover is vectors. So if you've learned about vectors, probably the first thing you hear is vectors have a magnitude and a direction. And this is true, right? If I say I'm going 50 miles per hour, that's a scalar. If I say I'm going 50 miles per hour north, now it's a vector. And to give you a visual example, take a look at that image that I have there of that red arrow. So it starts at the origin, the tail is at the origin, and the tip is at the point 2, 1. So x equals 2, y equals 1. And so you see the vector notation there where a equals 2, 1. So that is a representation of the vector a. It's a two-dimensional vector. And we know this because there's two elements, 2 and 1. And you see it in the image as well. That's flat, right? So as promised, I told you that vectors have a magnitude, right? So what is its magnitude? Well, the symbol for that, you see with those that pair of double lines, those double vertical lines around the A, that is the symbol for magnitude. And the magnitude of A is the square root of 2 squared plus 1 squared. So how did I know that? Well, you can think about this different ways. Honestly, that's the Pythagorean theorem, right? If I want to know the length of the hypotenuse, it's the square root of the one leg squared plus the other leg squared. So that's, it's Pythagorean theorem of just a right triangle there. But this property actually generalizes to any number of dimensions. If that was a 3-dimensional vector, I could have a third number squared and added inside of that square root. If that was a 20-dimensional vector, I would just have 20 numbers squared and added together under that square root sign. There's no limit to the number of dimensions you can put in a vector. And of course, the last line is just, 2 squared and 1 squared is 5, right? So it's the square root of 5. So as I just mentioned in that example, vectors can be 2-dimensional, 3-dimensional, or higher. There's no limit to the number of dimensions. One of the simplest things to think about is just positions, right? Like on that image there, that's a 2-dimensional space, and where are you on there? It's X and Y. It's a position. So that's one application of vectors. There's so many. I can't even list them all. There's a lot of applications of vectors. But if I was in a 3-dimensional space, I could name any point in the room as just 3 numbers, X, Y, and Z. That would define any point that I want. And in fact, there are even spaces. A type of Hilbert space has an infinite number of dimensions. So there's really no limit to the number of dimensions you can have in a vector. Another way to think about vectors is to think of them as an object that'll store a set of values, one value in each dimension. And those values, we call them elements, the different elements of a vector. And in computer programming, you'll see this a lot. Vectors are incredibly useful for storing these values. They can be added, they can be subtracted, multiplied by matrices, dotted with other vectors, scaled by a constant. There's so many operations you can do with vectors. We're going to talk about a few of them today, but we're just going to scratch the surface. And as I mentioned, positions can be vectors, forces, fluid flows, many other things that are tremendously useful. I couldn't come close to listing all the applications of vectors here. So I mentioned a vector dot product. So what is that? Well, let's look at 2 vectors here. We've got the vector A, which is 2, 1, and the vector B, which is 1, 1. And if I take the dot product of these with each other, what I mean by that is this. So you see how that we have the 2, 1 and the 1, 1, and the 1, 1, notice how I've flipped it. So now it is going, so this is called the transpose. So moving forward, we're going to talk about matrices that have both rows and columns. So real quick, since I mentioned a matrix, look at down there, that M equals 3, 4, 5, 6, right? That's a matrix. So that has rows and columns. So if you talk about the numbers going this direction, that's a column, right? Like columns of buildings. So then the other one is rows. So rows is going horizontally. So 3, 4 is row, 5, 6 is a row, right? That's row 1 and row 2. Or you can go in columns. You can say 3, 5 is column 1, 4, 6 is column 2, right? So if I take the rows and columns and basically I switch the number, right? So as I told you, this 5 here is row 2, but it's column 1. So if I switch that, and instead of being row 2, column 1, it's column 2, row 1, then it's part of the transpose. So that's just switching those around. So that's what I've done here for going 1, 1. So basically, instead of going horizontally, where effectively I have a single row with 2 columns, you could think about it that way, right? It's just 1 row, but there's 2 columns. Now instead, I've got a single column and 2 rows. So the row index becomes the column index, and the column index becomes the row index. So for now, suffice it to say that this row became a column. So now basically I take this 2, 1, and I go element 1 times element 1 plus element 2 times element 2, right? And I've kept the coloring consistent. So we have 2 times 1 plus 1 times 1, right? So this 2 times this 1 plus this 1 times that 1, right? And so whatever these vectors would be, this is how you take the dot product. Whatever numbers are here, and how they line up like this, you multiply together the numbers that have that same index, right? This is the first one, that's the first one. That's the second one, that's the second one. You multiply those together, and then you add them, and then that's your dot product. So this is the dot product of vector 2, 1 and 1, 1 gives you 3. So now matrix multiplication on a vector. Let's talk about that. So it's very similar. And so here I have this matrix M down here, 3, 4, 5, 6, right? And I'm operating on 2, 1 with that. So I'm multiplying this matrix onto this vector here. And notice again that, I've transposed it, so it's going vertically now. And so I want to sort of show you how these line up here. So remember for this one, how we kind of had this one, it kind of comes across, basically, if you think of the 2 and the 1, in my mind, I always think about it as like flipping it over, and I'll show you what I mean here. So if I take this first row and I flip it over like that, right? So 3, 4, and 2, 1. So the 3 goes with the 2, the 4 goes with the 1, right? So then that's going to be the top element here. So you see how that was kind of like doing a vector dot product using the first row only, right? Because that's kind of what we did here, right? 2 times 1 and 1 times 1. Add them together. Now we have 3 times 2 and 4 times 1, right? So that goes like that. And then the next one, to get this bottom element here, right? Same thing. So for me, in my head, whenever I do a dot product like this by hand, I always kind of have that motion in my mind. This is coming over and flipping over like that. So that's why I wanted to show you this before I actually write it out. So now if I write it out, basically we have 2 dot products effectively, right? This 3, 4 dotted with 2, 1 is this top, right? 3 times 2 plus 4 times 1. And then the bottom, we got this 5, 6 times 2, 1. So 5 times 2 plus 6 times 1 right there. And then if we simplify that, that's the answer. So if we do matrix multiplication with the matrix M on the vector A here, we get this vector out. And again, that is just barely scratching the surface on what you can do with matrices and vectors in that form. But I want to show you another way of writing vectors. And this notion is called the unit vector. So basically, notice how I have that X, Y, and Z. And that got that little thing on top like it's wearing a hat. We actually call that X hat, Y hat, Z hat. So X hat is the vector 1, 0, 0. Y hat is 0, 1, 0. Z is 0, 0, 1, right? So this is the X element, this is the Y element, and this is the Z element. And it's a unit vector here because basically, if you imagine this as an arrow, think in your mind, how do you think this would be pointing on our coordinate system X, Y, and Z if it's 1 in X and 0 in everything else? So if you're imagining an arrow laying right on the x-axis of length 1, then you've got it right. And then y is an arrow of length 1 right along the y-axis. Same thing with z. So we call these things, these are the 3 unit vectors in Cartesian coordinates, right? So Cartesian coordinates, this is our x, y, z coordinate system that we so commonly use. And this is how we write it as unit vectors. And so like, why would you do this? Well, being able to do algebra and calculus involving vectors is a really useful thing. And it's so much better if you can write it like this, right? Instead of writing this kind of bulky, like 1, 0, 0, 0, 1, 0 and all that, it's nicer if you can just write x hat. And I'm going to show you some examples to make that a little more clear. So let's say I have this vector all the way on the left here. It's the vector 2, 3, 4. And I want to do some algebra. So I want to write this in a more convenient way for doing algebra using the unit vectors x hat, y hat, and z hat. So instead of writing this vector 2, 3, 4, what if I take the 2 value, bring it out front here, the 3 value, bring it out front there, 4 there, right? So now it's 4 times 1, 0, 0 plus 3 times 0, 1, 0 plus 4 times 0, 0, 1. Right? And by the way, vectors, you can multiply them by a scalar. So this vector is 1, 0, 0. We're just saying multiply all of that by 2. So, okay, 2 times 1 is 2, 2 times 0, 0, 2 times 0 is 0. So this becomes 2, 0, 0. And then this one becomes 0, 3, 0. And this one becomes 0, 0, 4. So if we add all of these vectors together, right, they all have 0 everywhere except for one spot. So when you add them together, you're just going to get the 2, the 3, and the 4. That, you can multiply that 2, 3, 4 into it like that. I'm just trying to show you that this is all equivalent. So going back to this representation, well, 1, 0, 0, we just call that x hat. This is 0, 1, 0, that's just y hat. So this 2, 3, 4 right here, you could write this as 2x hat plus 3y hat plus 4z hat. And this is so much better to work with most of the time if you're doing algebraic manipulations. All right, up next, I want to talk about operators. So an operator in mathematics, it's funny, it's one of those things that like, you work with it, you know it when you see it, but to kind of put it into words is a little tough. And I felt a little better as I was working on these slides when I saw on Wikipedia the sentence that says, there is no general definition of an operator, but the term is often used in place of function, blah, 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 right? So I thought that made me feel a little bit better. But basically, it's something that operates on something to produce elements of another space, right? Like, the simplest operator you can think of would be like maybe like multiplying by a number, or, if you have a 3, I'm going to operate on that with a 5. Okay, well, now I have 5 3s, and now it's 15, right? That's an operation. So that's kind of one of the simplest ones. But kind of more typical operator that you would think of would be like the differential operator, taking a derivative. But first, let's talk about matrices as operators. What do you think? This matrix example that we showed, do you think this is an operator? Could we call that matrix M an operator? Yeah, of course. Yeah, we're taking, there's some vector 2, 1 right here, and we operate on it with this M, and then we get another vector out. So we mapped it from one thing to another. And so, this was just an arbitrary example of matrix multiplication. So I think this is kind of a more interesting matrix multiplication example. So this is something called a rotation matrix. So this is it applies an operation called a rotation. So let's start with the vector 1, 1. And so this vector, we look at that, and if we look at that angle right there, this is what pi over 4, right? Because this is pi over 2, that's pi. Yeah, that must be right. Or you might say like a 45-degree angle, right? So that's the angle it's at right now. Okay, so here's our rotation matrix. Notice how we have sine and cosine functions, and there's some value theta. That is the angle by which we want to rotate. So let's just say we want to rotate by pi over 2. So if we want to rotate by pi over 2, that's like 90 degrees. So we're gonna put pi over 2 in there for all of those thetas, and then our R matrix is gonna look like this, right? Because the cosine of pi over 2 is 0, the sine of pi over 2 is 1, and so that's why we get the values that we get here. But that's still our rotation matrix. That's just happened to be what values it holds if the angle is pi over 2. And so if we operate on this vector 1, 1, well, then we get this, right? This is that same process of doing a dot product. I want you to pause the video and make sure that this makes sense in your head, that you see the process of doing this matrix multiplication. And then we get this vector out. We get the vector -1, 1. And so if I look at that vector, right, it's starting at the origin, and then it points out to the point -1, 1. Does that look like it rotated 90 degrees? Yeah, it sure does. That rotated by an angle of pi over 2. So this is an example. This is a rotation matrix, and it's an operator. It operates on a vector and rotates it by whatever angle you plug in to that rotation matrix. So yeah, you can have operators that are based in matrices. They don't have to though, right? So you can have the differential operator, ddx. That's another example of an operator. So let's do an example with that. So let's say we have a function f of x equals x squared plus 3x, and we want to operate on it with ddx, and we want to operate twice on that same function. So that'll look like this, right? We have these two operators out there hanging out there, both kind of poised, ready to go operate. So let's have the first one that's right next to it go operate. So if we bring that one inside, we distribute it, ddx on x squared, ddx on 3x. Now we take those derivatives, we get this, and now we still have a ddx operator out there. So let's bring that one in. Let's distribute that operator through. And so now we're taking the derivatives of each, the 2x and the 3, and that's going to give us an answer of 2. And again, note that we distributed the differential operators one at a time. But could we maybe have just operated on the second operator with the first one? Sure. If you operate on ddx with ddx, you get d squared dx squared, and that is the second derivative operator. So now we're just going to apply a second derivative to the function. We distribute that through, and again, we get the same answer. And again, this was a simple example, but I just wanted to get you thinking about the differential operator in this way. All right, now we're going to be combining concepts. So we've got some unit vectors, right? So we've got x hat, y hat, and z hat. Those are in there. And we've got ddx, ddy, and ddz. And notice that it's the curly d, right? So that these are partial derivatives. So we're looking at multivariate functions, functions of x, y, and z here. And ddx here is only taking the derivative with respect to x, right? So that's what we're looking at here. And notice that each one is paired up with its respective unit vector. So all of this together, right, the sum of all these partials with their unit vectors is known as the gradient. And specifically, we're writing the gradient operator in Cartesian coordinates. It's different in other coordinates, and you're going to see that later. Also, just so you know, sometimes people will, instead of x hat, y hat, z hat, sometimes people will write I, J, K. You'll also see this frequently. So if you're looking at materials online or in your textbook and they use I, J, K, sometimes you'll see that, or often the I, J, K will also have a hat over it. But I just wanted you to be aware that there's different notations for this, but it all means the same thing. All right, so that is the gradient operator, but let's try applying it. So let's apply it to this function here, just a polynomial f of x equals 3x squared y minus 2x. So we're going to apply the gradient to that. So, and notice how I don't have to draw all these things out, right? I can just draw that triangle up there, which is called nabla. That's a Greek letter nabla. N-A-B-L-A is how it sounds, nabla. So if I apply that here, notice how f of x is not even a function of z. So any derivative with respect to a variable that's not in it is 0, right? Like if I say d dx of the number 5, what's the derivative of the number 5 with respect to x? Well, there's no x in that expression, so it's 0, right? And again, we know this. We can also think about it as like, okay, f of x equals 5. That's a flat line. That's flat. That slope is 0, right? So anyway, if there's no z in there, then all the derivatives with respect to z are going to 0 out. So we can ignore the ddz operator. And the other operators, we only need to care if that particular variable is in that term. So basically the distributive property, right? We can distribute this on all three of these, right? So basically ddz times z hat is going to operate on all this. And so is ddy y hat is going to operate on all of this inside the parentheses. And the same thing with the x term here. So they're all going to distribute through. But the only ones that are going to count are the ones that have the variable that the derivative is with respect to, right? So if you're taking ddy of 2x, that's going to go to 0, right? But if you're taking ddx of minus 2x, that one's going to hang out, right? That's going to be minus 2. So let's expand that. So here we have ddx of 3x squared y and times x hat. Don't forget the x hat, right? These things are part of the algebra, right? That's why we put them here. Okay, and now we've got ddx also acts on this one right here, right? This minus 2x, that also gets operated on. So we have ddx operating on 2x, and we brought the minus sign out front, and of course x hat, don't forget the x hat. And now we've got ddy of this 3x squared y that we have to care about, right? Because there is a y here, there's the y, so that's going to operate on that. And again, don't forget that y hat. All right, so they're all there, and now we can just take the respective derivatives, right? ddx of this is, okay, bring the 2 out front, that's going to be 6x, we'll leave the y alone, right? So there we have 6xy times x hat minus 2 x hat plus 3x squared y hat. So at this point, we've successfully taken the gradient, but we can make this a little nicer, right? Notice how we have two terms that have x hat here. So we can write it out like this. So there we have this term times x hat, this one times y hat. So now we have a nice algebraic expression that is in terms of unit vectors. They're still there. And so we can write this thing as a vector if we want. So going back, right? So we had this 6xy minus 2 times x hat and the 3x squared times y hat. And I want to write that as vectors now. So the way I could do that is like this. We could say, we could put this in our x hat. Remember, this x hat is the vector 1, 0, 0. And this y hat is 0, 1, 0. So if we multiply by those vectors and then add them all together, this part is going to be up top. This part is going to be in the middle. And then, so in this space, you know, nothing happened with z, right? There was no z. So z is just going to be 0 here. So I don't know, maybe it's just me. I find this really satisfying that you can represent vectors like this and go back and forth between this compact notation and the expanded one, you know, depending which one is best for your current use case. All right, we have made it to the end, folks. So thanks for sticking with this. I really hope this is helpful to anyone who's taking a physical chemistry course of any type. I think this should be a good refresher for anyone who's taking physical chemistry. And, you know, there's my website up there. Please, you know, subscribe, check out my videos, and I'll see you in the next one. Take care, everybody.